So now that we have some idea of how to work around with uncertainty, especially in the concept of capital budgeting, let's take a more deeper look about decision making under uncertainty. This is going to be important for us, especially when we consider things about studying insurance markets or about studying portfolio optimization and so on, right? So it's not enough to just consider the risk neutral world we are in, but we might need to investigate a bit more deeper about how to represent people's preferences about uncertainty. So this is a more general problem than the one we study in the world of finance. So it is there in generally about any economic systems as well. And the reason is pretty clear. It's because there are a lot of things that are uncertain in the real world, right? So imagine that you are a company which is in some particular industry, and you are kind of like have to use as raw material things that you are importing from abroad, right? So for instance, if you're in an airline industry, then clearly you would be concerned about what's the price of fuel going to be a few months down the line, right? Because you are giving out airline tickets that are being booked today at a certain price, right? So from your perspective, what's the price going to be, let's say 4 or 5 months down the line, is pretty uncertain. Then again, from an individual perspective, what's going to be your future wealth is also uncertain, right? So imagine that you are planning for your retirement. You put in some money in perhaps one of these mutual funds, but the amount of money that you are going to get typically will depend on market performance, right? So you have got basically an uncertainty about how much wealth you are going to have as you move towards retirement age. Then again, there might be uncertainty about whether commodities might be available for purchase in the future, and again, at what prices. And of course, more generally, you have a lot of uncertainty about the actions of other people. For example, what's going to be the government policy moving forward in terms of, let's say, the taxes and so on, right? So all of these are elements of uncertainty. However, in real world, if you have got individuals and companies making decisions, they still need to make decisions under this uncertainty, right? So we are going to think about how to go about modeling this particular situation. Now, what are rational responses to uncertainty? So we are going to study a lot of different things. So you might, for example, want to engage in some sort of risk management activities. You might want to kind of like spread your wealth across different assets or portfolios to try and reduce the uncertainty. The other thing that you might want to do sometimes is to buy insurance, right? So for example, insurance can be of different categories. You might have health insurance. So these are the type of insurance that pays out when you have any health related medical bills that come up. You might have auto insurance, which would, for instance, pay out when you have got damage to your car or your bike, let us say. And you might also have life insurance, which again pays out in particular cases, right? So one question is about this is basically you don't know what the future is going to be, right? Whether you're going to actually need health insurance or not, whether you're going to need auto insurance or not. So that depends on what do you think is the probability of you falling sick, or what depends on the probability of your car suffering damage and so on, right? But you have to make the decision about how much insurance coverage to buy before you actually know the future, right? So this is an example of decision making under uncertainty, and we'll use this as a working example to introduce you to the concept of how to think about modeling choices such as this, right? So one thing that is going to come up from our previous discussion this week is that we are going to be thinking of this as basically a portfolio of state contingent consumption goods. Now, that might seem a bit mouthful, so let us expand on it a bit, but we will soon see, I think, the connection with what we have been discussing. So let's consider the auto insurance example. So in terms of what are the different possible states of nature, in our very simplified world, there are only two possible states, right? So either you have a car accident, we are going to refer to that as state A, or you are not going to have a car accident, we are going to refer to that as state NA, right? And imagine that an accident occurs with probability pi A, and it does not occur with probability pi NA, right? So these are things that are known to us. And of course, because you have got that these are the only two possibilities, so therefore pi NA must be equal to 1 minus pi A. And imagine that if there is an accident, that's going to cause a loss of wealth to you of amount L. And this L is something that you know for certain. The only thing you don't know is whether an accident is going to happen or not, right? And hence, the probability distribution reflects that uncertainty. Okay, so what do we mean by state contingent. So basically, as you recall from before, this means that you have got payoffs which depend on what the state realization is, right? So for example, state contingent contract is one, which is going to be implemented only when a particular state of nature occurs, right? So insurance is an example of a state contingent contract because the insurance payout happens only if the accident happens, right? And if the accident does not happen, then the insurance would not pay you out, right? Similarly, you can have something like state contingent consumption plans. So this would be, for example, you make a plan depending on, let's say, whether you get a bonus or not, or whether you do not have accident or not, and then you decide, okay, I'm going to go take a vacation or not, right? So this would again kind of like be based on different states occurring, and then based on that, what is your plan, right? So these are all examples of state contingent ideas. Okay, so let's go back to this insurance problem. So typically, whenever we are thinking about decision making or choice under certainty or uncertainty in economics, the way we go about doing it is that we think about what's the set of feasible choices that are available. And then among the set of feasible choices, what's the best option that some individual can choose, right? So here we'll proceed in the same way. So first we'll think about what's the set of feasible choices. So that's going to be described in the state contingent budget constraint. And once we have an idea about that, we will think about what are the different preferences over these possible options that are available, right? So in order to discuss the state contingent budget constraint, suppose that each unit of additional insurance coverage costs gamma. This is, again, gamma is a parameter that is known to us. And imagine that a consumer initially has M units of wealth. Okay, so we are going to denote the consumption in the no accident state as CNA, and the consumption in the accident state is denoted by CA. Okay, so one option that is always available to the consumers, and of course it depends on the law. So in some places where you might live in, it might be compulsory to buy insurance, but let's discount that feature for now. So imagine that a consumer has an option of buying not any insurance. In this case, basically, what will be the consumption in the two different states? So if there is an accident, then this consumer suffers a loss of a wealth L. So therefore, the consumption in the state of accident is going to be M minus L. Remember that M is the initial wealth that the consumer have. And if there is an accident, you have got M minus L. And if there is no accident, then the consumption in that state is going to be equal to the wealth, right? Equal to M, right? Now, this is, we can represent this graphically as well. So on the x-axis, we have got consumption in the state where the accident happens. And on the y-axis, we have got consumption in the state where the accident doesn't happen. So this option M, M minus L. So M minus L again corresponds to the consumption in the accident state, and M corresponds to the consumption in the no accident state. So this option we are going to imagine that is always available, right? This is the case if the consumer does not buy insurance. Now, what the ability to buy insurance does is that it allows you to actually transfer wealth across different states, right? So let's think about how that happens. Imagine that you have decided to purchase K units worth of accident coverage, okay? So because the cost of purchasing 1 unit of accident coverage is gamma, so if you purchase K units, therefore your total cost is gamma K, right? So this is basically the insurance premium, right? Now, this insurance premium has to be paid before you know whether the accident has happened or not, right? So what that means is that doesn't matter what the state of the world is, this is something that is going to be subtracted from your wealth because you have chosen to purchase this amount of insurance, right? So this gamma K that you see here, right? You can notice that you're subtracting it from your wealth in both the states, and this corresponds to the premium that you are giving to the insurance company. Okay. Now, if the accident does not happen, this is the only transfer that you are going to do. So therefore, your consumption in the state where the accident does not happen is given by M minus gamma K, where gamma K is the total premium that you have paid to the insurance company in order to purchase this insurance coverage, right? In the state in which accident happens, there are going to be two additional things, right? So you have the initial wealth M, right? Then the accident is happening. So therefore, you are incurring this loss of L. you have paid the premium gamma k, right? And the good thing is that if you have paid the premium gamma k, then you are going to get back k amount of money if the accident happens, right? So that's the advantage of purchasing insurance, right? Clearly from here, you can see that gamma needs to be between 0 and 1 in order for you to actually purchase the insurance, right? Okay, so we can eliminate actually k from this pair of equations, and we end up getting, if you do the algebra, you'll end up getting an expression like this, right? So what this is saying is that you have basically got a negative relationship between consumption in state A and consumption in state not accident, right? Why do you have a negative relationship? Basically, the idea is the more insurance you are purchasing, you are basically transferring your wealth from the no accident state to the accident state, right? So in order to get one more unit of consumption in the accident state, what you need to do is you need to purchase additional insurance. But you have to also factor in that you are paying the premium in both the states, right? And so therefore, what this equation is saying is that in order to get one more unit of consumption in the accident state, you have to give up gamma by 1 minus gamma units of consumption in the no accident state, right? You should actually also go through this calculation once to understand intuitively why you have this expression of gamma by 1 minus gamma as the slope, okay? So that's the interpretation of slope. And so basically, this is what you have in terms of the feasible choices that are available to you, right? This is the budget constraint. So recall our discussion when we discussed feasible sets and in week 2. So this is the corresponding budget constraint that you have here. Okay, so these are the feasible choices. Now we need to think about what are your preferences over these choices, right? Because the underlying theory that we always kind of like think about is that the decision maker is going to choose his or her most preferred alternative from those available to her or him, right? So what we need to think about is that basically how much does consumer care about consumption in the different states, right? Clearly, the consumer cares about consumption in the accident state versus the consumption in the no accident state. So the more the consumption that this person gets, the happier this person is, right? So we need to find an analytical way of representing that. And in economics and finance, we often use what is known as utility function to describe the consumer's preferences over the different options, right? So for now, just think of this utility function as a measure of satisfaction or happiness, right? And as we have argued, this should depend on both the amount of consumption that you get in the state of accident, as well as the amount of consumption you get in the no accident state, right? And higher the values of CA and CNA, happier off you would be, right? Now, another thing to note, if you think about it a bit more, is that not only do people care about the consumption in the different states, but how much they care about the consumption in each state would also depend on what they think is the likelihood of that state happening, right? So, for example, imagine that you think it's very, very, very unlikely that an accident is going to happen, then probably you do not care so much about consumption in the no accident state, right? You would value much more about what your consumption is in the accident state, right? So what that says is that the utility function that we have, right, that should depend not just on the two consumptions in the different states, but it should also depend on the probability of the different states happening, right? So more generally, we write this utility function for consumption in the states as a function of consumption when accident happens, consumption when accident does not happen, probability of accident happening, and probability of accident not happening, right? So this is like at a very abstract level. This is one way of representing people's preferences over the different consumption plans. And basically what it comes down to is that you want to have this value of the function as high as possible, given your constraint about what are the choices that are available to you, right? Okay, so one particular example of such a function is given by this that you see here, where the utility function takes the value pi a CA plus pi n a CNA, right? So if you think about it, pi a is, remember, the probability of the accident happening. CA is the consumption if the accident happens. Pi na is the probability of the accident not happening, and CNA is the consumption of the state where the accident does not happen, right? So this is basically nothing but the expected value of consumption, right? So this is saying that this is the average value of consumption that one would get. And this is in some sense what we have been discussing so far, right? When we have been saying that, the world that we are dealing with is risk neutral. And so we only want to evaluate things as per the expected amount of money that we are getting from a project and so on. And we do not care about the risk and so on. So this is basically the world in which we are operating, right? Now, it turns out that uh, often we would need to go beyond just thinking about maximizing expected amount of money that you are getting or expected consumption, right? So in order to see this, let's look at a very classic example, right? So this is actually an example from a game that was described more than a few centuries ago, right? So let's look at this game, and this is actually an interesting example to think about why you might want to go about beyond just maximizing the expected payoff. So imagine that you have a game involving a fair coin. Remember that a fair coin is a one where the probability of heads and the probability of tails are both equal to half. So we are going to toss the coin once. If the coin lands with heads on top, then the participant is going to receive a prize of 2 rupees and the game is going to end there. Okay. On the other hand, if the game is actually such that the first toss is going to result in tails, then we have to continue the game. Okay. So then we are going to toss the coin a second time. And if on the second time, right, the coin toss is heads, so the first one is tails and the second one is heads, then we are going to give the participant a price of 4 rupees and then going to end the game here, right? But suppose that the second toss is also tails, right? So the first toss is tails, the second toss is tails. Then we are going to again continue and toss the coin again, right? So if it happens that you have the getting the heads for the first time on the third toss, then the participant is going to receive a price of 8 rupees and the game ends here. However, if it is tails again, then again we will continue to flip the coin, right? So we are going to continue playing this game till the first head is obtained. If the first head is arriving on the end toss, then the participant receives a prize of 2 to the power n rupees. We are generalizing what we have been discussing, and we are going to end the game right there. However, if it is again tails, we'll continue to play on game time, right? So at this point, you might want to just pause the video and think a bit more about if you were to be the participant in this game, how much would you expect to win in this game? Okay, so let's look at the answer. So suppose that X is a random variable, which denotes the amount of money that the participant wins in this game. Okay, so what are the possible set of values that this X can take? So if the game ends on the first toss, you are going to get 2 rupees. If the game ends on the second, you are going to get 4. If it ends on the third, you are going to 8. If it ends on the fourth, 16. If it ends on the 5, 32, and so on, right? We can also calculate the probability that X takes any of this particular value, right? So for example, X will take the value 2 if you have a heads on the first toss. So this happens with probability 1/2. X is going to take the value 4 if you have a tails in the first toss and heads in the second. So this happens with probability 1/4 or 1/2 square. More generally, X is going to take the value 2 to the power n if you have got tails in the first n-1 tosses and heads on the nth toss. And again, this happens with probability 1/2 to the power n, right? So we can then calculate what's the expected winning. So this is the same as calculating the expected value of X. So if you now do the calculation, this is going to take the value 2 into half plus 2 square into 1/2 square plus 2 cube into 1/2 cube, so on, plus 2 to the power n, 1/2 to the power n, and so on, right? This is an infinite series where each of the terms is equal to 1, right? So therefore, the expected amount of money that a participant would expect to win if they play this game is actually infinite, right? Now, this is very interesting, right? Because suppose that we were with the world where we only care about the expected amount of money that one were to get, right? So in that case, probably since the expected amount of money that you are expected to get is infinite, if somebody had said, okay, why don't you pay 50 million rupees in order to play this game? Then that person should have been willing to say, yes, I'm willing to pay 50 million rupee, right? Because why? Because even if you pay 50 million rupee, then your expected winning net of the amount of money you pay is still infinite, right? Because it's infinity minus 50 million, so that's still infinity, right? However, in reality, if you think about, suppose you were the one who were playing to play the game, would you be willing to pay 50 million rupee in order to play this game? Probably not, right? So that is where kind of like the kind of like this thinking starts, that maybe something is going on, which is a bit deeper than just kind of like evaluating different uncertain situations as per the expected amount of money that you expect to get, right? Let's look at another example. Maybe this will help to actually illustrate some of the ideas. So inherently, perhaps one of the reasons why you were not willing to pay in 50 million rupee in order to play that game is that you might have thought that, okay, there's this good chance that the first toss is going to end up coming as heads. And then therefore, I end up getting only 2 rupees, for which I have played 50 million rupees, right? So perhaps you have a dislike of risk, right? So we want to consider now another example where this question of whether you like or dislike risk comes up, right? So imagine that you're a consumer who currently has 10 units of wealth and is contemplating playing a gamble or a lottery that is going to give him a 50% probability of winning 5 more units. So then his wealth will become 10 plus 5, 15, or a 50% probability of losing 5 units compared to his original 10 units of wealth, right? So that his wealth will end up becoming 5 units, right? So here the uncertainty is about his wealth. If he ends up taking this gamble or lottery, then he has a 50% chance of ending up with 5 units of wealth and a 50% chance of ending up with 15 units of wealth. If he does not take up the lottery, then he knows for sure that he's going to have this 10 units of wealth, right? The question is, should he take up the gamble? Now, here again, if the person only cares about the expected value, then the person should be indifferent, right? Why should the person be indifferent? Because if he does not take up the gamble, he's going to get 10 for sure. If he takes up the gamble, his expected wealth is going to be half of 5 plus half of 15, which is also equal to 10, right? So the expected value is the same regardless of whether he takes up the gamble or not, right? So then the person should be indifferent. But what if the person likes or dislikes risk, right? Where is the risk? The risk is coming from, if you take the gamble, you have the possibility of potentially ending up higher, but you also have the potential of ending up lower, right? So there is this uncertainty or risk. And suppose you also have an opinion about that, right? Apart from just caring about the expected value, then what should be your preference between taking up the gamble versus not taking up the gamble? So motivated by this, let's kind of like pursue our previous analogy, right? So we already have in mind that we care about not just the consumption in the two states, whether I win or lose, right? I care about the probability of the two states as well, right? So one example that we have discussed so far is, you just care about the expected amount of money that you have, right? So this is the example where you have got the utility given by pi1 c1 plus pi2 c2, right? Now, if you think about it, we can actually generalize this example and think about utility as pi1 multiplied by u of c1 plus pi2 u of c2. So this example that we just had discussed previously is a special case where you have got u of c is equal to c, right? But more generally, when we write this utility as pi1 uc1 plus pi2 uc2, what do we mean by that? So basically what we are saying is that we can write utility as a weighted sum of some function of consumption in each state, right? The state in which you are winning the lottery versus not winning the lottery, for example, or if you are insurance, an accident or not an accident, right? And we are going to weigh your consumption in each state by the probability of each of these states, right? So for example, one way to think about this is that suppose that pi1 was certain to happen, then this u of c1, c2, pi1, pi2 would just become u of c1, right? So then basically it's the utility of certain consumption in state 1. Or if you have pi2 equal to 1, so therefore pi1 is equal to 0, then you have got uc2 is the utility of consumption in state 2, right? So what this is saying is basically this is the weighted average or the average utility of the consumption in the different states, right? And whenever we write utility in this form, we are going to say that this is an example of an expected utility function, right? Why is it expected utility? Because this is the average utility level you're going to get across the two states, right? Okay, so let's now use this framework to think about this question about should you take up the gamble or not. So what we need to do is basically, if you are going to be using this expected utility criteria, we need to be comparing the expected utility for the two scenarios, right? So if the person does not take the gamble, then in doesn't matter what the state of the world is, the person is going to get 10 for sure, right? And if this is the expected utility criteria, then it doesn't matter whether state one or state two happens, you're going to get 10 for sure. Then this is pi one u of 10 plus pi two u of 10, right? So pi one plus pi two is equal to 1. So you end up that this person is going to get an expected utility equal to u of 10, right? What happens if you do end up taking the gamble, right? So in this case, pi 1 is the probability that you end up winning. So this is equal to half, in which case your wealth is 15. And if you end up not winning, which again happens with the probability half, your wealth is going to become 5. And so therefore, this is your expected utility, right? So it comes down to a comparison of U10 versus half of U15 plus half of U5, right? So these two actually have meanings, right? U10 is basically the utility of the expected value of the wealth, right? So the expected value of the wealth in this example is half of 15 plus half of 5. So that's equal to 10, right? So if you get the expected value for sure, that's U of 10 versus the average of the two numbers U15 and U5 if you take the gamble, right? So these are basically your wealth across the two different states, right? Okay, now let's think about which one is higher. So the first thing to note is that if you had UC as a linear function, then these two will always give you the same value. Okay, you can do the calculation. Suppose UC is A plus BC. You can compare what happens at U10 and what happens in this case. You'll find that doesn't matter what the value of A and B is, you are always going to get the same answer for the two expected utilities. And in this case, when you have got UC is a linear function, we are going to say that the consumer is reasonable, right? So in this case, the expected utility of the wealth is going to be the same as the utility of its expected value. And in this case, the consumer doesn't care about the riskiness of the wealth at all, right? So the consumer only cares about the expected value of the wealth. However, you can have other cases. So for example, suppose this u is a strictly concave function, which means that its slope gets flatter as the wealth is increasing. Then you can show that we are going to have u of 10 is going to be strictly greater than half of u15 plus half of u5, right? And this will be a scenario where we would say that a consumer is risk averse, right? So this basically means that the expected utility of wealth, right, which is this expression, is less than the utility of the expected wealth, right? So when would you have UC as a concave function? We know from calculus that this would, for example, be the case if the second derivative is negative, right? So one particular example is UW is equal to log of W, but you can have other examples. So for example, UW equal to square root of W also is an example of a concave function. And in general, the more concave the utility function, the more risk averse the consumer will be. We can also represent this graphically. So what you have is, remember, you have this initial wealth of 10, right? And you have a choice of either sticking with that 10, right? And this is the utility function that is given here. So if you stick with 10 for sure, then this is the amount of wealth that you are going to have, which is 10. And so therefore, you can read from this function that your utility is going to be given by u of 10, right? On the other hand, if you decide to play the lottery or the gamble, you're going to either end up with 5 or 15. If you end up with 5, your utility is going to be U5. And if you end up with 15, your utility is going to be U15, right? And your expected utility is going to be basically represented graphically by the midpoint of the line joining this U5 and U15. So that is the half of U5 plus half of U15. That's the graphical interpretation. And if this U is a concave function, then this U10 is always going to lie above this half of U5 plus half of U15, right? So this is the case corresponding to the risk averse case, right? Notice that here, as we discussed, your slope is getting flatter as the wealth increases, right? And that basically means in calculus terms that the second derivative of the U function that you have is negative. But that's not the only thing that can happen. So you can also have the opposite case where you have got U is a strictly convex function. So what that means is that this slope is getting steeper as the wealth increases. In this case, what we are going to get is that U of 10 is going to be strictly less than half of U15 plus half of U5, right? And we would characterize this as a scenario where you have got that the consumer is a risk lover, right? So this basically means that a consumer prefers a random distribution of wealth over getting its expected value for sure. And again, a twice differentiable function is convex if its second derivative is positive. So one example is u of w equal to w squared. And in general, the more convex the utility function, the more risk-loving the consumer will be. So we can also represent this graphically. Here we have an example of a utility function which is convex. So again, we can do the same analysis that we did before. So you decide not to take the gamble, you get 10 for sure. And this is your utility u of 10. You decide to take the gamble, either you're going to get 5 or 15. So you get either u5 or u15 with equal probabilities. So therefore, your expected utility is again given by the midpoint of the line joining u5 and u15. So this is the point. And we can see here that for a convex function, u of half of u of 5 plus half of u of 15 is going to lie strictly above u of 10. And so therefore, you would prefer to take up the gamble rather than actually getting this 10 for sure, which happens if you decide not to take the gamble.